In this video, we're going to look at some common power functions that are of a negative and fractional order. That is, we're going to have a look at the rectangular hyperbola, so that's your 1 over x. We're going to look at the truncus, 1 over x squared. We'll look at the square root function, which is x to the power of a half, that being the fractional order. And we're going to have a look at the cube root function as well. So there's a little bit of background information, but generally when we see what we might call the standard equation for the hyperbola, our value a here represents the dilation from the x-axis. This is effectively going to tell us the shape of the hyperbola. If a is positive, then we can recall that it looks something like this. If a is negative, then we would have to reflect about the x-axis. We can see that it would look more like that. We can think about h as being a translation along the positive x direction or along the positive x-axis, and k is our translation in the positive y direction. So we'll have a quick look at what that looks like. So using our Desmos calculator, we can see here that we've got the graph of 1 over x. So this is your basic rectangular hyperbola. Now, what I've done is I've set the value of a to be equal to 1, the value of h, and the value of k to be equal to 0. But watch what happens when I start changing the value of a. So as a increases, we can animate that now. You can see that that's going to stretch out. And in fact, it might be worthwhile zooming in. Zooming out, I mean to say. And you'll notice as a becomes negative in value, this graph reflects about the x-axis. And so the shape is fundamentally changed. So we'll just set that back to 1. There we go. And watch what happens when we alter h. So altering h will change where the x-asymptote is. It will also, more formally, translate this function along the x-axis. So if we set h back to 1, back to 0 I mean to say, there we go, and this time we'll alter k, we can see that k is always going to be our y asymptote. That's simply because this plus k represents the fact that we're translating along the vertical axis, or translating in the y direction. So this is how our basic hyperbola operates, but we can go into this in a little bit more detail. So whenever we're looking at the graph of y equals a over x minus h plus k, so we're talking about a hyperbola here, we can look to this number up here, and we might just do that in blue for consistency, but we can see our general shape. The thing that matters here is whether or not this is going to be reflected, or whether or not it's just going to be a positive hyperbola. So this number up here will tell us about the shape. If we look to the bottom there, and we've got x minus h, it's generally okay to say that the vertical asymptote will be at h. But we might, I suppose, more generally define this if we had something like 4 over 2x minus 1. Because we've got a value 2 here, it would not be fair to say that the vertical asymptote was at x equals 1. And so more generally what we can think is take the bottom bit and make 2x minus 1 not equal to 0, because we know we can't divide by 0. So if I brought that 1 over, 2x cannot equal 1, and x cannot be a half. So I'd be saying that my x asymptote would be a half in this case. So just be careful when you read that the vertical asymptote is at x equals h. This is only true when the coefficient of x is 1. Now the horizontal asymptote will in fact always be k, so that's always going to be there. Now let's have a think about why this is. Suppose we had 1 over x plus 1 equals y. Now let's look what would happen if y was equal to that positive 1, was equal to this asymptote. So I had 1 equals 1 over x plus 1. When I subtract 1 from both sides, I get 0 equals 1 over x. Now I can't possibly start with something, a quantity 1 in this case, divide by something else, which is my x, and have the answer 0. That doesn't make sense. If x gets really, really big, then 1 divided by a million, for instance, is going to be really small, but it will still be a millionth. It'll still be something. 1 divided by a trillion will still be a trillionth. And so this is a statement that doesn't make any sense. And that's why we'll always have k as the horizontal asymptote. And regardless of if there's a coefficient for x or not, we'll always know that k is that horizontal asymptote. So this is a good little cheat sheet to follow. We can have a look at what that looks like in practice now. We're being asked to determine the equation of the hyperbola shown. So let's look at what we know. We know, first of all, that we have an x equals 2 as our vertical asymptote. Our horizontal asymptote is y equals negative 4. So if I start with my very basic equation, y equals a over x minus h plus k, I now have some values for h and k. So we could say y equals a over x minus 2 plus negative 4. So that's going to become minus 4, and we'll sub in that 2 just so you can see where everything's coming from. Now, I've still got this a, and this dilation factor. I'll need some other piece of information in order to solve for it. What I notice is that I'm also given the point 0, 0. Now we can read that coordinate as though we're saying when x equals 0, y equals 0. So if we start off with what we had, y equals a over x minus h plus k, we then said, oh, well, h and k are going to be 2 and negative 4 respectively. And now I know that when x is 0, y is also 0. So this is giving me an equation that I can solve. A over negative 2 is still going to be a over negative 2. Minus 4 equals 0. So if I add 4 to both sides and multiply by negative 2, we can see here that a is equal to negative 8. Now that makes sense when we look at the shape of this graph, because the standard hyperbola we would have thought would have looked like this. But we can see that our shape is quite different, and so we should have expected a negative. Finally, it's important that we actually answer the question. The question wasn't find the dilation factor. The question was determine an appropriate equation. And so we would put that in context and say, okay, y equals negative 8 over x minus 2 minus 4. Now that's all well and good when we're given something in standard form. But what happens if we're asked to obtain the maximal domain of this function here, which is not in standard form? Well, the domain is actually still going to be found in the same way. If I had y equals some function, in this case 2x plus 5, divided by another function, in this case x plus 1, it has to be true that x plus 1 can't be equal to 0. That is, it has to be true that the bottom function can't be equal to 0. So here I'll know that f of x is x plus 1, so x plus 1 can't be 0, and x can't be minus 1. So to state this in a more formal way, we would say x is an element of reals, but not negative 1. So we're then asked to sketch the graph of this odd function and also state its range. Well, I have no way to sketch the graph when it looks like that, so instead I'm going to practice actually dividing this through. So you remember from last year, if I had 2x plus 5 divided by x plus 1, we can go about doing this with polynomial division. If I start off with my first term, 2x divided by x is going to be 2. So I'm simply just dividing the first thing. Then we'll multiply. So let's multiply 2 by that divisor. So 2 times x is 2x, 2 times 1 is 2. So we divide, we multiply, and then we subtract. So if I'm subtracting, 2x minus 2x is 0, that's what I thought we'd get. 5 minus 2 gives me a positive 3. So what we're saying is, when we take 2x plus 5 and we divide it by x plus 1, it goes in twice with 3 remainder. Now let's take something like 9 divided by 4. Imagine we said 9 divided by 4. Now back in primary school you might have said, oh, 4 goes in once, it goes in twice, and there's 1 left over. And so you'd say, oh, well that's twice and a quarter left over. Because you take your leftover bit and you put it over the divisor. Well, in algebra nothing changes there, of course. And so we're going to say that this goes in twice with 3 remainder. Now 2 and a quarter is the same as we're saying it's 2 and 3 remainder. So that's how we go about dividing. So what I'm saying is that that original function, 2x plus 5 divided by x plus 1, is actually the same as 2 plus 3 over x plus 1. And in this regard, I've put this in a standard form, in something that I can sketch. So if we start with y equals 3 over x plus 1 plus 2, might be a bit clearer now that that's in standard form. I've got an x asymptote at negative 1 and a y asymptote at 2. So I can see here, x can't be negative 1, y can't be negative 2. So at this point I'd probably sketch my axes, make sure that you use a ruler. I can't quite do that on this. And we want to make sure that we've got x equals negative 1, so that's down here. Oops. And we've got y equals negative 2, which is down here. So they're 2 critical points that we've labelled, but like always, we also need to find the intercepts. So we can find the y-intercept by letting x equal 0. Well, the y-intercept is equal to 3 over 0 plus 1 plus 2. Now I've just noticed here, I actually made a mistake. The y-asymptote can't be positive 2, of course. So I'll just quickly fix that up and put a positive 2 here. Those kinds of transcription errors where you write from the line above happen all the time, so it's important to try and catch those. Apologies about that. But my y-intercept, 3 divided by 1 is 3, plus 2 is going to be 5. So that makes a lot more sense. Got this point here, which is x equals 0, y equals 5. Now I can see the shape of this should look something like this. And that means that the reflection should look like this, and there's certainly going to be an x-intercept. In order to find this x-intercept, we'll let y equal 0. So 3 over my x-intercept plus 1 plus 2 equals 0. Bring that over. 3 over the intercept plus 1 is negative 2. Now this negative 2 is kind of like writing negative 2 over 1. And if we wanted to solve this, well, we could raise both sides of this equation to negative 1. In other words, we can flip both fractions. So I could say that x plus 1 over 3, so I flip the left-hand side, isn't equal to negative 2, it's equal to negative 1/2, so I flip the other side. If I multiply by 3, x plus 1 is negative 1.5, and if I minus 1, we'll get negative 5 on 2. So there's our negative 5 on 2, or negative 2.5, and 0. Now, I've got my asymptotes. I've got 2 points. Those 2 points actually do show this dilation factor of 3. So I'm fine. If I only had 1 point, it would be wise just to sub in another point in order to show that dilation factor. The next type of function we're looking at is the truncus. Now the truncus is exactly the same as the hyperbola, except in shape. But everything else that we look at is very similar. We can still think of it as being this standard form, where we've got our translations and our dilation factor. One of the key differences here is that the domain is going to be very similar to what it was, where it's reals but not h, or reals but not something. But the range, in fact, is quite different. Because the truncus always travels in one direction, rather than having a range that is reals but not something, you could also see that the range would be either something to infinity or negative infinity to something. As we're talking about range, I've just realized that I didn't appropriately answer this question. Back here it said to sketch the graph and state its range. Looking at it here, the range is reals but not 2. Apologies for that one. So let's look at how we sketch the truncus. Here I've got y equals 2 over x minus 2 squared plus 3. So starting with what I know, I could think that my x asymptote is going to be 2. So x can't be equal to 2. My y asymptote is going to be 3. So y can't be equal to 3. And my shape is a positive 2. So my shape should look something like that. It is really important that we use a ruler for this. So we might actually jump over to the whiteboard app in order to sketch this properly. Okay, so once we think about what we know, it's a good idea to actually draw in those asymptotes. So we'll get out our ruler. Now I know that y can't be equal to 3, so I'll draw that asymptote. Here we can see y equals 3. My x asymptote is at x equals 2. And the general shape is a truncus, so it should look like this. So I can see that there's still a y-intercept to find. Well, in order to find that, we'll let x equal 0, as so. So I've got 2 over negative 2 squared plus 3. Well, negative 2 squared is just 4. So 2 over 4 plus 3, well, that's a half plus 3. That is 3.5. So I can put that in here as 0, 3.5. So sorry, that's 7 over 2. Now finally, it's really important that our truncus is actually mirrored. So I want to make sure that I've shown that. In fact, if you look closely at my graph, this distance is not exactly the same as that distance. So I want to make sure that I'm showing to the examiner that my shape is correct, at least in an abstract way. Well, my asymptote is 2, so x equals 2. And if I move 2 to the left, the height is 7 over 2. So I'll simply move 2 to the right now, which jumps me across to here. So 2 to the right would be 4, and the height has to be the same to show that this is mirrored. I might also make sure to take care to label x, y, and the equation y equals 2 over x minus 2 squared plus 3. There's 3 more examples here, and there's a few things that are different. They might have been reflected about the x-axis, there might even be a dilation from the y, could even be that it's been reflected about the y-axis. But what you need to do is give these 3 a go, so pause the video here, try these 3 questions, and we'll do the solutions in a moment. Okay, so starting with what we know, we can see here that the graph has actually been reflected. So there's a negative 3 at the top there. That's telling me that my general shape will now go down as it approaches that asymptote. I can see that my vertical asymptote is at negative 2, and my horizontal asymptote is at negative 1. So I think x equals negative 2 and y equals negative 1. Let's start with the y one. So just down here, that's going to be y cannot be negative 1, and x I know cannot be negative 2. So x can't be negative 2. We actually write that asymptote as x equals negative 2 and y equals negative 1. I know that my general shape will look like this. And so once again, there is no x-intercept. What I do have is a y-intercept though. So in order to find that, my y-intercept, I'll let x equal 0 minus 1. So that's negative 3 over 4 minus 1. Well, that 1 could be written as 4 over 4, and we end up with negative 7 over 4. So here, when x is 0, y is negative 7 over 4. Once again, that 0, that x equals 0, is 2 units away from the asymptote. So I can find a corresponding point, which would be 2 units in the other direction. So from negative 2, we go 2 units this way, and we end up with negative 4, negative 7 over 4. I've got my asymptotes labelled, I've got a critical point labelled, and another point for dilation. The last thing to label are my axes and my equation. Now in this example, we can see that there's actually a reflection about the y-axis. And so we need to consider that that bottom bit cannot be equal to 0. So in other words, 1 minus x squared cannot be equal to 0. If I square root both sides, and if I bring the x over, we find that it's actually a positive 1. So what we're saying here is that that asymptote is where x equals positive 1. So we've got a vertical asymptote here. I really should be using a ruler. And we've got our y asymptote at negative 1. So this is going to be a little bit different because I can see my shape is positive because this is a positive 3. I don't know if this is going to cross the y-axis down low or if it's going to do so up high. So before I do this, I might look to find my y-intercept. Remember, I can do this by letting x equal 0. So y equals 3 over 1 minus 0 squared minus 1. Well, that's just 1 squared. So this is just 3 take away 1, which is going to be a positive 2. So it's important that I did that because I can see that this will be a positive 2. Now to sketch my shape. Looks something like that. And it needs to be reflected on the other side. So in order to show the shape, I know that this 0 is 1 unit away, so I'll go 1 unit in the opposite direction, and I'll say that that's 1, 2. I'm still missing these critical points, and I can find those by letting y equal 0. So 3 over 1 minus x squared minus 1 equals 0. Bring the 1 over. 3 over 1 minus x squared equals 1. Remember, I can raise both sides to the power of negative 1, or I can flip both sides. So 1 minus x squared over 3 is equal to 1, because if I flip 1 over 1, it's the same thing. And 1 minus x squared equals 3. You can square root both sides. 1 minus x is plus or minus root 3. And if I bring that 1 over, and multiply by the negative, x is positive 1 plus or minus root 3. So this here will be 1 minus root 3 and 0. This will be 1 plus root 3 and 0. Just make sure you also label things like the equation and the axes. There we go. For our final task, I've already put in the asymptotes here, but you can see that my h value is negative 3 and my y value is negative 4. My a is negative 1, and so this is a graph that will go down with time, or down as it approaches that asymptote. So when I sketch that, you can see that I don't need to bother trying to find x-intercepts. I do have a y-intercept, and I will need to show the dilation point. So to start off with, y is negative 1 over 2, 0 plus 3 squared minus 4. So that's negative 1 over 2 times 3 squared over 2 times 9. We got minus 4. So negative 1/18 minus another 4. So 4 times 18 is 72, and this will be negative 1/18 minus 72 on 18 I mean to say. So I end up with negative 73 on 18. So that's this here. Now, the equidistant point from that asymptote, so this was 3 units there, so 3 units in the opposite direction, will give me negative 6, and that corresponding height of negative 73 on 18. This is a good way to show that you've definitely got the right shape. We can label our x and our y and our equation. Y is negative 1 over 2, x plus 3 squared minus 4. Okay, we're nearly through this. So we've got square root and cube root functions to go. Now, the square root function looks pretty similar to something we would have seen last year, and it's just that endpoint followed by an arcing shape. It can have that standard form, just like we saw in Year 11, and so all we need to think about is that is that number that's outside the square root, is that positive or negative? If it's negative, then we would have rotated about the x-axis, or rather reflected about the x-axis. This h gives me the endpoint, because it tells me it's been translated to the right, and this k also gives me the y value of that endpoint, because it's been translated up or down. So the important things to consider, I'll zoom in on this here. The endpoint is hk, the domain is h to infinity, that's in standard form, but really we could think of the domain by saying x minus h has got to be greater than or equal to 0. Can't have the square root of a negative. And we know that the range will be from k to infinity, assuming that a is positive. It'll be from negative infinity to k if a was negative. So there's a few ways to look at this, but generally if we think of it exactly the same as we thought of it as the truncus, but it has a different shape, and it has an endpoint instead of an asymptote, we should be fine. The cube root function is something new. It looks very similar to that square root function, if we think this part looks very similar, but it also has a tail. Now this is because we can do this, the cube root or the odd root of a negative. All the same things apply, it's just that the shape is a bit different. So we still need to think of it as a x minus h plus k. Rather than being an endpoint, it's a point of inflection. So let's have a look. State the maximal domain of y equals 4 minus x and square root minus 1. Well, remember that if y equals the square root of 4 minus x minus 1, the issue is that this inside bit, this 4 minus x, that has to be bigger than 0 or equal to 0. So 4 minus x is greater than or equal to 0. If I bring the x over, 4 has got to be greater than or equal to x. So if 4 is bigger than or equal to x, the biggest value x can have is 4. So another way of writing that is to say the domain is equal to negative infinity to 4, because the biggest value x could have is 4. Then it's asked me to sketch the graph and state its range. Well, it is a square root function, and we might actually do this on the whiteboard again, just because it's a bit smoother for the video. Okay, so the first thing I see is that I've got a minus x. So imagine that this was the square root of negative x plus 4, so just change the order, haven't changed the value, minus 1. Well, I want to take that out as a common factor. So this is now the square root of negative x minus 4 minus 1. So I'm hoping you can now see that my endpoint is that x equals positive 4 and y equals negative 1. So I've got x equals positive 4, y equals negative 1. So that's the endpoint of this graph. What's a little bit hard to see, because you wouldn't have seen it last year, is that this negative here reflects my general shape. Rather than being there, it reflects it about the y-axis. So it now reflects this way. And so this graph here, rather than going up and to the right, will go up and to the left. So I can see that there are both x and y intercepts to consider. Well, if y equals the square root of 4 minus 0 minus 1, then we've got the square root of 4 minus 1, which is plus or minus 2 minus 1. Now I know it's not going to be negative 2 minus 1, because it has to be positive from my shape, so I ignore that solution and I say that y equals 1. So that's where you need to look at your graph and look at the general shape in order to infer the right answer. So we've got 0, 1. There's still an x-intercept to be found. So if I said the square root of 4 minus x minus 1 equals 0, so let y equals 0, I'll bring the 1 over. Square root of 4 minus x equals 1. I'll square both sides, and so 4 minus x equals 1. If I bring the x over, bring the 1 back, I'll find x equals 3. So that gives me 3, 0. Now we're almost done. Best practice just to label our axes and label our equation. So I'll show you how the different values of a and n, so these different values of that might cause reflections in the x and the y, would change the general shape of the curve. So what you can see I've done in Desmos is that I've plugged in the general equation, and we can now play around with the value of a. So when a is positive and increasing, you can see that that graph is going to jump up and it's going to increase at a much faster rate. But when a moves into the negatives, we start to reflect. So imagine here I had a equals negative 1. You can see that that reflected the original graph. Now, if we flick it back to our normal one, this time we'll play around with the value of h. Now this will change the endpoint. So that's going to move the graph to the right and to the left, or parallel to the x-axis. So we'll flick that back over to 1, or to 0 rather, and k this time, this is going to shift the graph up or down. So you can zoom out a little so you can see it, but this is translating in the y direction. Now the interesting thing to consider here, so just bring that back, is what happens if there was a negative, like we saw. And put brackets over here. What happens if we change that to put a negative? Well, you can see that it goes in the opposite direction. So it's reflected about the y-axis. And if I made my a value -1, we'd flip it down there. So there's a little bit to consider with these graphs, and we'll do a quick show of what this looks like all on one graph. So suppose we had our standard case, y equals a times the square root. This time I'm going to say that there's an n outside, so there's that dilation from the y-axis. Now imagine that everything is positive. So I've got a is greater than 0 and n is greater than 0. What I'm going to have is a graph that looks like this, and we've got h, k. Let's imagine this time that n was negative. Well, if n was negative, we multiplied it through, we might have something like a outside the square root of negative x minus h plus k. Well, now this whole thing is going to be flipped over to this side and move in the opposite direction. This time I'll have negative h, k, because if I tried to take that 1 as a common factor, I'll end up with x plus h inside. So this is the case where we've got a negative in there. Suppose that I had both of these things being negative. So there's a negative outside the square root and a negative inside. So we might think negative a square root of negative x minus h plus k. Then I'll have negative h, negative k. And if we just had the case where it was a negative a, but no negative inside here, then we would have rotated, or reflected rather, about the x-axis. So we'd go down there. So this is our general types of shapes that our square root function might take. It's important to be able to look at it and infer which direction it will behave in. For our final example here, we're told that the graph of a cube root function, so immediately I might think, oh, well that's a outside the cube root of x minus h plus k. So the graph of the cube root function has a point of inflection at 1, 5. So that means that my hk equals 1, 5. So I've already got two values there. The graph cuts the y-axis at the point 0, 2. So what that tells me is that when x equals 0, y equals 2. What we're being asked to do is determine the rule of this function, sketch the graph, and state the domain and range. Well, in order to determine the rule, I'll start with my standard. So the cube root of x minus h plus k. Because I already know h and k, I'll immediately replace them with 1 and 5. So I now need to find my value for a. The way to find that is to know that when x equals 0, y equals 2. So y is 2 when x is 0. So we're asked to find the cube root of negative 1. Well, that's just negative 1. So negative a plus 5 equals 2. I just changed that over. I like to work left to right. Bring the 5 over. Negative a is negative 3, and a equals 3. So my equation here, y equals 3 outside the cube root of x minus 1 plus 5. We also need to sketch the graph and state the domain and range. So in order to do this, I'll jump back into the whiteboard app. So we know we've got a nice positive shape. So this is just going to look like that elongated S, and an endpoint at 1, 5, or rather a point of inflection at 1, 5. So at 1, 5, I've got this point of inflection. It's certainly going to go up and over, but I need to know if it will go this way or if it goes further down. So the best way to do that to finish off this shape will be to use the y-intercept. Y is 3 times the cube root of 0 minus 1 plus 5. That's negative 3 plus 5, which is 2. Now, we were also told this in the question if we paid close enough attention, but it's good to verify it all the same. So this now will go like this. So we get 0, 2. Our final critical point is just over here. It's that x-intercept, which we find by letting y equal 0. So 3 times the cube root of x minus 1 plus 5 equals 0. That means the cube root of x minus 1 is negative 5 on 3. And if I cube both sides, x minus 1 is negative 25 on, negative 125 over 27. Now if I'm going to add 1, it's like adding 27 on 27. So x is equal to 152, that's a negative. So in fact I'm adding 1 to that. So adding 27 on 27 gives me negative 98 on 27. And so we've got negative 98 and 27 and 0. As usual, make sure that we label x and y, which is there for us. Y equals 3 times the cube root of x minus 1 plus 5. The last part of this question was to give the domain and range. Well, the domain of y is equal to reals, which is usually the case unless we've got a restricted domain. But with a cube root function, the maximal domain will always be reals. The range, if we look at this function, also goes down to infinity and up to positive infinity. And so the range of y is also equal to reals. So we've looked at a lot this lesson, but most of it is all stuff you've seen last year, and it's just going to take a little bit of practice to get it right. If we can think of things in terms of our general equations, so our general equations can be thought of as y equals a over x minus h plus k. So that's my hyperbola. I've got my truncus, which is very similar. It's x minus h squared plus k. We can think of our square root function, a outside of x minus h plus k, or our cube root function, which is a outside of the cube root of x minus h plus k. Now, we can always look at the value a for our shape. So that's going to give me the shape. But I might also make sure that the coefficient of x is positive if I want to keep this simple. We can find our endpoint or our asymptotes, in other words, our unique critical points, by examining h, k. A lot of this will come down to practice, so make sure you do that and let me know if you've got any questions.